You're welcome. Any more homework? Last class, conditional expectation. So first of all, we have conditional density functions or probability mass functions. So this is just the conditional probability that x takes a value little x, conditioned on knowing what the value of y is, that y is little y. And that is just, you look at the joint probability mass function divided by the probability that y takes a value little y. Similarly with density, you look at the joint density divided by density of y.
This is for conditional
Probability mass function and
Oh.
conditional probability.
Oh, conditional expectation.
Conditional expectation now is if I condition on, I want the expected value of x, condition on knowing what the value of y is. So that is just going to be
Like the first thing that you wrote with the line under it, conditional x.
condition on
No, the up to the upper left, conditional x.
expectation.
Oh, okay. That is like, oh, okay. Okay.
Or depending on whether it's discrete or continuous, it's x. And then I said that if I just want to find the unconditional expectation of x, what I could do is, so this conditional expectation of x, essentially you would integrate out your x and you'd get it to be a function of little y, right? So little y appears at the end. So you can think of this conditional expectation, it depends on what value y takes, right? What you're assuming y takes. So you can think of this as a function of y. If you're looking at the unconditional expectation of x, it's basically going to be, you take your conditional expectations and, so to find the expectation of x, you'd say, okay, the expectation of x, if you knew what y was, is this, but there was a probability that y takes this value, is this. So I weight each of these functions with the probability that y takes the value little y. And take the sum of that. And that would give me the unconditional expectation. Similarly with in the continuous case, I weight this function with density. So this is a discrete case, this is a continuous case. So in a problem where you're given your conditional if you know your conditional expectations and you know these probabilities, you can get the unconditional expectation. Because you're saying that to find the expected value of x, say y takes a value little y with this probability, and then with this probability, your expected value of x takes this value. That's one way to think of it.
So for both those continuous ones, like the conditional one and the unconditional one. So for the first one, condition. We have it from negative infinity to infinity, but in reality, or in practice, we'll actually be using the x,
yes,
like domain.
I'm looking at the expected value of x here.
Right. So,
and y is fixed at y. So we're integrating with respect to x.
And then for the one at the bottom,
here,
we'll be using y's.
We're using y's because now it's like I don't know the value of y. Y can take different values with these probabilities, right? So with this probability, my expected value of x is this quantity. Okay? So you basically have to calculate this first and then plug into this formula.
Oh, okay.
Or you also know this. The unconditional expectation of x, if you knew this is just x, right? This is another formula that you could use if you only knew this information, if you knew the conditional expectation. If you know the marginals, you might as well just calculate it like this, or summation. So you know these formulas, right? Now, just to prove that both of these give you the same thing, let's look at this. If I look at summation over all y's, so if you are not convinced that these two are the same thing, give you the expected value of x. So this is the definition of expected value of x, and I'm going to prove that this formula is also just expected value of x. So let's look at this formula. Plug in what the definition of conditional expectation is. That is just conditional expectation of x, if I know y is given to be little y, is just summation of x, and I multiply it with this, right? But now, what is this conditional probability? This is just my joint probability divided by this, and I multiply it with this thing. So then these two cancel out, and you're just left with so you're left with summation y, summation x, x, p of x, y. Let me interchange the x and y's. So x, I can pull that out of summation over y, and I get. But what is this? This is just px of x. I've summed out our y's. And this was our definition of expected value of x. Do the same thing with integration. You see that basically this is the definition of expected value of x. But if you use this formula, you see that it basically gives you expected value of x. So this is to convince you that this formula actually gives you expected value of x. So if you take the weighted average of your conditional expectation, you get the unconditional expectation. So basically, if you want to find expected value of x, you sum over x, and you sum out all your y's when you multiply it with the joint probability mass function. All right. So that's conditional expectation. All right. So we did one example where I first asked you to find the conditional expectations, and then I asked you to find the unconditional expectation. There were two ways you could have found the unconditional expectation. You could have first tried to find the individual probability mass functions and use this formula, or you could have taken, which is the method we used, we took the weighted average of our conditional expectation. All right, let's do another example where you see that this formula is very useful. So here's a miner is trapped in a mine containing 3 doors. The first door leads to a tunnel that will take him to safety after 3 hours. So it leads to some exit. 3 hours of travel. The second door leads to a tunnel that will return him to the mine. After 5 hours of travel. The third door also leads into a tunnel that will return him to the mine. After 7 hours of travel. If we assume that the miner is at all times equally likely choose any one door. What is the expected length of time until he reaches
Does the miner know all the information?
yeah, I mean, so the information is that he knows that there are 3 doors.
He just knows there's 3 doors.
Yeah.
Okay.
And
He doesn't know the
yeah.
hours or anything.
Right.
Okay.
I mean, but even if he did, see, this is this clause that I put in. I'm saying that we should assume that every time, no matter what information he has, he's equally likely to choose each door.
Okay.
So I mean, yes, maybe he's incredibly stupid, doesn't mark the doors that he's in. I mean, so when ignoring all such possibilities, that he puts a mark on the door he's gone into, and then when he comes back.
The likelihood of him choosing the first door again is equal to him choosing the second door.
Right. Yeah. I mean, yeah. He's always going to choose each door with equal probability.
He doesn't like get tired and walk slower the second time.
No.
That's amazing.
Okay, the problem is
Impressive.
exactly as it is written down here. In the sense, he always does that first route in 3 hours, the second route in 5 hours. We're talking about a machine, basically, okay? A machine that tosses like a 3-sided die every time he has to make a choice between the doors, and always takes 3 hours of travel through the first tunnel, 5 hours through the second tunnel, and 7 hours through the third tunnel. Okay?
3-sided die.
Yes, and he doesn't mark the doors, so he doesn't get more information the second time round or anything like that. Let's assume maybe it's dark and he's not able to see any markings on the door.
I can't,
All right, so
I can't
keep this in
visualize
mind.
a 3-sided die.
Oh my God, we're going off on a tangent here. All right.
In C4.
In fact, we're making the problem quite simple by saying that at each time, basically this is like the worst case scenario, right? That he doesn't ever learn, that he's just going to keep leaving it to chance that he will finally get out of there. Okay. And well, you could think that maybe he might be trapped there forever, right? He can just keep taking doors 2 and 3 and just keep coming back. But even if he chose these doors at random each time, how likely is that to happen? Say, so at each time that means the probability of him taking a door that brings him back there is 2/3, right?
Right.
Now, say he chooses the wrong door 3 times in a row. That with what probability does that happen? 2/3 cubed. He chooses the wrong door 2/3, with probability 2/3 the first time round. Second time round is again independently, so 2/3 times 2/3. So if I say in 10 times he chooses the wrong door 10 times, that means it's 2/3 to the power 10. Now 2/3 is a fraction, so this is going to become a very small number. So the probability of him staying trapped forever now it becomes very small, because it means he takes the 2 wrong doors infinitely many times. Okay, and that probability becomes 2/3 to how many ever times he goes. Takes the wrong door. So you see that yes, there is a possibility that he will take the same doors, but that probability is getting very small. Okay? And we know that once he takes the right door, he exits. So there's no question of coming back.
Mm.
Right. So if you want to think about what could happen, either he takes the right door the first time around, and after 3 hours he's out, or he takes one of the wrong doors, he comes back, and then the question is again, which door do you take? So basically, when he comes back to this crossroads of 3 doors, it's back to the same situation. If at that point in time he's looking at what is his expected amount of time till he exits, it's the same as when he first faced these 3 doors. Okay. All right. So if this is case, and actually you get a kind of recursive formula in this, so this is how you should think of solving it, and it becomes really simple, and the idea is using conditional expectation. What are we conditioning on? We will condition on his initial choice of door. So first of all, let x be the amount of time till he exits mine. Exits mine. He reaches safety. And let y be choice, initial choice of door. And I only need to know about the initial choice of door. Let's set this up. All right. Now, if he chooses the first door, what's the expected amount of time he takes to exit?
3 hours.
He just takes 3 hours. Oh, let me drop the hours. So this is amount of time in hours. Now, if he had chosen the second door, what's the expected amount of time? So he definitely takes 5 hours, first of all. So it's 5 hours, and that brings him back to, the initial point again, right? And then he's faced with the same question, what is my expected time till exit? Okay? So the time until exit now is just this. Okay? So we want to find the expected amount of time, right? So this is when you're starting out, you're at this point where you have 3 doors and you ask how much time until I exit, expected amount of time until I exit. So when I come back, the amount of time until I exit is again the same because I'm back in the same position, right? So basically, in the initial time when I take the second door, I travel definitely for 5 hours, so I have to add 5 hours, and then it's the same expected amount of time. What happens if I choose 3 the first time round? What's the expected amount of time? You definitely travel 7 hours, and then whatever expected amount of time. And now we weight this with the probability of choosing each of these doors. So if
So
I'm
do we call, I'm sorry,
Yeah,
do we
so-
call this definition, this initial definition here, just e to the x? Because you referred to that when you have 5 plus e to the x?
Yeah, so e to the x is the expected amount of time until I exit, right?
Okay.
Not conditional on anything. So when I'm back at my initial point, I still have a choice of 3 doors. I can choose any one of them, and so I can do all this whole
okay,
thing.
okay.
So expected value of x.
Mhm.
Now, if I definitely choose door 1, I know the expected value of x.
And we-
Condition on that.
E to the x is different than e to the x.
Condition, right, no,
Right,
yeah.
right,
So
okay.
e to the x is the
I think that's
unconditional one.
correct.
You haven't yet made your choice of which door. Okay? So if the first time around you made the choice of door 2, you walk a distance for 5 hours, and then you have to look at your expected amount of time until you exit, where you haven't yet made any decision. Okay? You're brought back to the original point. The expected value of x is basically, this is my expected value, but the probability of, I weighted with the probability that I choose this tunnel, door 1, or I choose door 2 with this probability, and then I'm faced with this expected value, or this is my expected value condition if I chose door 3, and this was the probability I chose door 3. And each of these cases, I say these are all 1/3, these probabilities. So it's just going to be 1/3 the expected value of x conditional y equals 1 plus the expected value of x conditional y equals 2 plus the expected value of x conditional y equals 3. Alright, so let's plug in what we know about these conditional expectations. This was just 3. This was 5 plus the unconditional expectation of x. This was just 7 plus the unconditional expectation of x. So what do I have here? I have 1/3, I plus 7, 12, so 15, right? 8. Plus 2 expected value of x. Over 3 plus 2/3 expected value of x. Equation with so you have expected value of x equals 15 over 3, which is 5, plus 2/3 expected value of x. So subtract, you get 1/3 expected value of x equals 5. So even if you're incredibly stupid and just keep taking like the same probability in any of the doors with 1/3 probability, the expected amount of time you will travel until you exit is just 15 hours. So even this strategy of just blindly picking each door with probably 1/3 doesn't have such a long expected wait until you exit.
No, that's a long time.
Yeah, but this is an expected value, so you could be one of the unfortunate few who ends up with something which normally should happen with very small probability, but it could happen to you. So, but the expected value is about 15 hours. Okay. So this is an example where, I mean, so you could use this way of getting expectation by taking the average of your conditional expectations. It's a pretty useful method of calculating the expected value. So we have just about 2 more weeks of classes, right? Mm-hmm. Yeah. All right, so with this, we're done with conditional expectation. So the remaining topics that are left are, I'll talk about, so we've talked about expected value of sums of random variables, and now I'm going to talk about the variance of sums of random variables, or variance of functions of 2 random variables, and covariance of, which I haven't defined covariance before, so covariance would be something new. After that, next week, I'll define something called moment-generating functions, and then we'll use that to prove a very important theorem in probability, which is called the central limit theorem.
What?
The central limit theorem.
Oh.
In fact, there are 2 very important theorems in probability. One is called the law of large numbers, and the other is called the central limit theorem. And we'll do both. So some of this is going to be a review about properties of expectation and variance. So you are familiar with some of this. So we're going to talk about expectation of a function of 2 or more random variables. Of covariance. Variance of sums of random variables and correlation. Now, expectation of a function of 2 random variables, I think I've defined this before, but if I haven't, in the discrete case, it's basically fxy double summation over x and y. It's the same idea as expectation of 1 random variable, but function of 2 random variables, so you use your joint probability mass function. So this is the discrete case, and the continuous case. Now some simple properties. Some of these we've talked about before. supposing I had a single random variable. So let me write this down as E1, properties of expectation. The expected value of AX plus B, it's just A times the expected value of X plus B. A and B are constants. Property 2. I don't know if I need to write this separately, but the expected value of a constant is just constant. Expected value of X plus Y. If I have two random variables, X and Y, is just the expected value of X plus the expected value of Y. Or I can generalize to expectation of x1 plus x2. So if I add up n random variables, it's just going to be the sum of their expectations. A simple proof of this is look at the discrete case. Summation for x, so expected value of x plus y. I just sum this function x plus y. That's a definition. So I can write it as I can distribute the sum. Here, if I sum over all y, I can pull this x out, and basically I have summation over x. Summation over y, this just gives me px of x, right? And similarly here, this term just gives me py of y. So I'm left with summation over x times px of x, with summation over y times py of y, and that, by definition, is expected value of x plus expected value. And you can generalize this to n, sum of n random variables. So, that property, if everybody, your random variable x always takes values greater than or equal to y, then the expected value of x is always going to be greater than the expected value of y. And, the idea is if x minus y is greater than 0, that is positive only if x is greater than or equal to y. So with 0 probability, your random variable x takes values less than y. So look at the expected value of x minus y. If it's sum over all x, sum over all y, x minus y. Now we know that this is non-zero only when x is greater than y, so only when this is negative. And if x was less than y, this probability is 0. So when I say this is greater than or equal to 0, I mean I only consider values of x greater than y.
I think you use P instead of R in the proof.
I'm sorry, can you say that again?
In the beginning you used R. Oh no, that's P of x. I see.
Yeah.
That you were using.
The joint probability mass function, so this non-zero probability is only given to values where x is greater than or equal to y. With probability 0, x takes values less than y. Alright, so therefore, this is just expected value of x minus expected value of y. So expected value of x is greater than or equal to expected value of y. That's just the proof of this fourth property. What else do we need? I'm going to write this down. It should be obvious that x minus expected value of x, that's just, because it's just value of x minus constant, expected value of x minus expected value of x, which is 0. Some more properties. The last property, if x1, x2, xn are independent, then the expected value of their product, 1 times x2 times xn, is just the product of their expectations. So the expected value of the sum is the sum of the expectations, whether these random variables are independent or dependent, doesn't matter. But for product, the expected value of product is the product of the expectations only if they are independent. And the proof of this, in fact, I can prove something more, we can prove something more general than this. I think we've proved this before. Position. If x and y are independent, then the expected value of g of x times h of y, so in particular you can have g of x as x, h of y as y, so the expected value of x times y will just be g of x, h of y. Let me call this proposition. The proof of this, I think you know that if x and y, so I'm going to either prove it for the discrete case or continuous case. Which one should we do? Continuous, discrete? Continuous. So in the continuous case, if they're independent, what do you know about their joint probability density function? It's just the product of the individual probability density function. So let's look at expected value of g of x times h of y. It's just the double integral of g of x times h of y, joint density function. But we know that this f of xy is just product of f of x, y. I can just club together the x terms and the y terms. Fine. So your x term and y terms separate out nicely, so you can integrate out the x term separately and the y term separately. And this is just expected value of g of x times expected value of h of y. So basically that tells us that the expected value of x1 times x2 is just the product of the expectations if x1 and x2 are independent. And then you can continue and generalize this to n random variables. So for n random variables, the joint density function of x1, x2 up to xn would decompose into the product of the individual density functions. And then this the same thing here. You would combine all x1 terms, all x2 terms, and you get products of these intervals. Alright, so these are properties of expectations. You need to know them to simplify problems and calculations. Okay, so that's expectation. Let's recall some of the properties of variance. Once again, when I talk about expectation, it's this one number that, one value that gives you some idea of this random variable. Okay? Its mean value, its average value. Once, say you have the expected value of x, you know that your random variable x takes different values with different probabilities. And expected value of x is a value about which the different values of x are centered. So how spread out are the values of x from its mean value? So say x could be a random variable that takes 3 different values. Say it takes the value x1, x2, and x3. Say it takes this value with probability 1/4, this value with probability 1/2, probability 1/4. Then if you look at the mean value of x, it's going to be 1/4 times x1 plus 1/4 times x2 plus 1/2 times x3. So clearly the mean value cannot be out here, because it's taking the average of these 3 values. So it must be somewhere out in this interval, right? There's more weight given to this x3 value. So that means it pushes the mean. Clearly the mean can't be out here, okay, because there's more weight given to this value. So say your mean must be something like,
what is that, 1/6, 1/4? That's one?
so x1 takes, so say my random variable takes the probability, takes the value x1 with probability 1/4. That's what I've written down. Probability of x equals x2, 1/4, and probability x takes the value x3 with probability 1/2. Then the mean value, which I will denote by mu, typically that's the notation for the expected value of x. So the mean value mu is, say, somewhere out here. But we know that it takes values other than mu, right? So how spread out is it from mu? We know that we can't, so if we look at the distance of x from mu, so mu is the expected value of x. If I just look at the expected distance, that would average out to 0. So I need to do something better to get an idea of how spread out these different values are. I will look at the square of the distance. And the reason why the expected distance is just 0 is because this difference would be positive, but this would be negative, and they would cancel out. So if I take the square, then I add up this distance, and on average, how far is your random variable x from this distance? With probability 1/2, it differs by this distance. With probability 1/4, it differs by this distance. With probability 1/4, your x differs from mu by this distance. So that's what your variance of x tells you. It gives you some idea of how spread out your values of x are from the mean, which is where it's centered. So, so this would be summation x minus mu. So that's your variance of x, or I could just write it as the expected value of x minus mu. That gives you an idea of how spread out it is. What are some of the formulas or properties we know about variance? So we know that one property, so first of all, variance is defined as the expected value of x minus mu squared, where mu is the expected value of x. The first property is we have an alternate formula that we can use to calculate variance, and that is expected value of x squared minus mu squared. So remember, my mu throughout is expected value of x. The second property is if I'm interested in the variance of this new random variable, ax plus b, so I take x, I scale it by a, and I shift it by b. The shift in the variance doesn't matter, because if I just shifted everything by b, my x by b, this whole picture just shifts by b. but how spread out you are from mu, mu also shifts to mu plus b, and how spread out you are is still the same. Okay? Its distance from mu is just a relative distance, right? So that doesn't change. But scaling by a does. Okay? So if I scale this by 2, the distance between these two expands, right? Becomes by a factor of 2. So variance by definition x minus mu square. So if I'm squaring this, changes like this. So basically, if I take standard deviation of x to be the square root of variance of x, then the standard deviation of ax plus b scales by a standard deviation. A times the standard deviation of x. So if you know the variance of a random variable x, then the variance of a random variable 5x, you know that too. That would be 25 times the variance of x. Of course, if I have a constant, its mean value is b, and it doesn't deviate at all from b, so its variance is just c. So variance is a measure of how spread out it is. Now once you have mean and variance, so this gives you some information about your random variable x. Say if you didn't have the probability mass function, probability density function, if you had at least the mean and variance, that's some information. Now if I have another random variable, y, I would like to know how x and y, their relation in some sense, some measure of their relation. So if I have two random variables, x and y, what I'm interested in is I can come up with a measure that measures how much, if x increases, does y increase or does y decrease? That is, do they move in the same direction or in opposite directions? Okay? So maybe I can come up with some kind of measure for that. So, and for that I can define something called the covariance between two random variables x and y. And I can define it like this. X minus the expected value of x is the deviation of my random variable from its mean. I multiply it with the deviation of the other random variable from its mean and look at the expected value of this function. So what does this mean? If, say with the, so this value could be positive or negative. When would this be positive? If with a high probability, when x is above its mean, y is also above its mean. That means they move in the same direction. Or when will this product be positive? When this is positive and this is positive, or both are negative, right? So both are positive means they both are above their mean. Both are negative means they're both below their mean. So if with a high probability both are positive at the same time or both are negative at the same time, it means they're moving in the same direction, deviating from their means at the same time. If this is positive and that's negative or vice versa, that means when x is above its mean, y is below its mean. So the deviations, they deviate in opposite directions. And that would lead, if this happens with high probability, then I say, then you get negative covariance. So covariance measures the relationship between x and y, and it tells you whether x and y move in the same direction or in opposite directions. So clearly, if covariance of xy is positive, you can conclude they move in the same direction. If covariance of x and y is negative, it means they move in opposite directions. So there are some things that make intuitive sense. If I tell you that x and y are independent random variables, then the movement of x should not affect the movement of y, right? So in a sense, you should expect the covariance of x and y. If x and y are independent, what do you think the covariance should be? It should be 0, and it turns out it is 0. So why does that happen? So some properties. If x and y are independent, so maybe I can make another note here. You can say something like this. Means x, y is positive, means x and y deviate from their means in the same direction with high probability. Covariance is negative, it means with high probability x and y deviate from their means in opposite directions. So basically, how do they co-value? Okay. Proof of this. So if x and y are independent, why is the covariance 0? So recall that if x and y are independent, what do we know? We just proved that this is just expected value of g of x times expected value of h of y, right? So if they're independent, expected value minus expected value of x times y minus expected value. So expected value of a function of x times a function of y by independence. This is just the expected value of x minus expected value of x times the expected value of y minus the expected value of y. Expected value of x minus its mean is just 0. The expected value of y minus mean is just 0. Second property, as in the case of variance, you have an alternate formula given like this. Here too you have an alternate formula. Alternate formula for covariance. Covariance of x, y. I'll leave that as an exercise for you guys to do. So use your definition of covariance, multiply out the terms, take the expectation, use the properties of expectation, and you should end up with this formula. You can already see that sometimes that should happen. When you multiply these terms, you get x times y. minus expected value of x times y minus expected value of y times x plus product of the expectation. So when you take the expected value of that, it should simplify to this. For computations, this is a much nicer formula. Right. Property. You can call this the symmetry property. That is, covariance of x and y is the same as the covariance of y and x. So the order in which we take it doesn't matter.
So the symmetry property?
Yeah, symmetry. So if instead of x, y, you have y, x, it doesn't matter because you look at the definition, the order in which you multiply things doesn't matter. So what's the covariance of x and x with itself? Look at the formula, what do you get? You just get the formula for variance of x. So the covariance of x with itself is just the variance of x. And of course it has to be positive because the x deviates from its mean. X deviates from its mean, so they move in the same direction. Alright, what else? Covariance of ax comma y is a times covariance of xy. It makes sense if you have ax minus expected value of ax, you can just pull this a out. Last property. Covariance I equals 1 to n. This is just the summation of I. And this, if you just put it into this formula, then there's this question of multiplying things out, and then you basically get this result. Okay. All right. But as a consequence of this, so the proofs of all these things, they're fairly simple. Proving symmetry, proving this, or this. Consequence of this is the following. You can use, let me put this in as another property. Supposing I ask you to find the variance of the sum of random variables. So what sort of formula would I get for this? So here I can just use all your earlier properties and get this. So maybe I won't put this as another property. So I can simplify this formula as follows. Variance I can think of as covariance of this thing with itself. This is using this property, property 4. And now by property 6, I can write this as summation I equals 1 to n, summation I equals 1 to n, covariance of xi and xj. Now, as I goes, oh, maybe I should have this. Oh, I can write this as j. Basically, this is the sum of these. The sum, the same sum here. I'm just using a different index so that you can distinguish between the two. Now, some of the terms that I multiply would be x1 is multiplied with itself, x1, right? X1 can get multiplied with x2, with x3, etc. Now, when xi is multiplied with xi, then you have covariance of xi, which is just the variance. So if you look at all the combinations of terms along the diagonal of this I and j matrix, you have variance of xi, variance xi. And the off-diagonal elements, when I is not equal to j, you have covariance of xi, xj. Either you can write it as the sum when I is not equal to j, or by symmetry, sum only over all I less than j. Because when j is less than I can just flip that around, it's the same thing. I have that. Exactly. So it's basically the sum over all I less than j plus the sum over all I greater than j, but the covariance for xi, xj when I is greater than j is the same as when it's flipped around. So it's just adding that twice. So you can memorize this formula. That variance of summation, the sum of your xi's.
That's an I less than j?
I is strictly less than j, yeah. When I equals j, that's already considered in the sum of the variances. I don't consider I greater than j because I've put this 2 here. I add up twice in case when I less than j. So this is your formula.
Is there supposed to be one more closing parenthesis, or is that supposed to be after the x?
I'm sorry, say
They're supposed to be in their closing. Oh, right there. Okay, gotcha.
Variance summation, write the summation I equals 1 to n, variance of each xi plus twice summation less than j. This is the formula that we're using. If x1, x2, xn are